Dear students, in this class I am going to talk about the another type of data converter, that is digital to analog converter, R2 ladder type DAC. There are three types of digital to analog converters we have in the syllabus. One is weighted resistor digital to analog converter, and the next one is added to our ladder type DAC we are going to discuss now. And the next one is inverted R2 ladder type DAC. From these three digital to analog converters, we can expect the one long answer question in the external examinations. Not only in the external examinations, this topic is very important in the internal examinations. I'm going to ask the one question in the out of three digital to analog converters, such as weighted resistor digital to analog converters, R2 ladder type digital to analog converters. Next one is inverted R2 ladder type digital to analog converters. So in the previous class we have studied about the weighted resistor digital to analog converter. It has some of the advantages and the disadvantages also. So if we discuss this advantages of digital to analog converter, that is a weighted resistor digital to analog converters, it is very simple to analyze. That means when the switch is connected to the reference voltage, that is when the switch is connected to the reference voltage, the bit value, binary bit value is 1, we can assume. When the switch is open to the reference voltage, then we can consider that bit value 0. That is very simple to analyze that circuit. And it immediately provides the conversion from the digital to analog. So that is weighted resistor digital to analog converter offers the fast conversion. Rate of conversion is very fast. Disadvantages, anyone can easily understand the disadvantages. That means as the number of bits increases in the digital data which we wanted to convert to the digital to analog, then the wide range of resistors also we needed. If it is having the 4 bit of data, then we have to go with the resistor values R, 2R, 4R and 8R. That means what? As the number of bits increasing, then we require the wide range of resistances. So by having that content in the mind, and we can understand, if I'm having the 10-bit digital data, and if you wanted to convert that is into the analog form by making use of the weighted resistors digital to analog converter, it requires the resistances from resistance value R to the, that is 1024 times of R. That means what? 10 different types of resistors we need. R, 2R, 4R, 8R, 16R, 32R, 64R, 128R, like that, 128, like that. We can have the wide range of resistors. And coming to here, this is offering the very simple analysis, because when the bit is 1, so that we can consider it is on. When the bit is 0, we can consider is half. So that means what? Whatever the switches, that is switches we have been using in the weighted resistors, we have to use that switches with the low resistances. Immediately it has to switch from on to off to on. So usually it is limited to the 8 resolutions only. That means you can go with the 3 bit of data used to be converted into the analog form. So that 8 resolution means we can have the bit size is about the 1 by 2 power of n minus 1. All these things we have discussed in the previous classes. So As a weighted resistor, digital to analog converters requires the wide range of resistor values like R, 2R, 4R, 8R, etc. For the 10-bit of digital to analog converter, we have required the resistors from R to, that is 1024 R. So therefore, the largest resistor is about 1000 times the smallest one. These wide range of resistors are impractical in the fabrication of integrated circuits. The voltage drop across the large resistance is more, which affects the accuracy of digital to analog converter. As the value of the resistance increases, then the voltage across that resistance also increases, because V is equals to I into R. V is directly proportional to R in that case. If the R increases, obviously V also increases. Then the voltage drop across each resistance increases such that we cannot expect the accurate signals at the output side. Accuracy is going to be affected by making use of the weighted resistor digital to analog converter, because as we are going with the more number of bits in the digital data, then we have to go for the wide range of resistances. To avoid the disadvantages of having the wide range of resistance, we have to go for the another type of digital to analog converter, that is called R to 2R ladder type DAC. It uses only two resistors. Instead of having the wide range of resistors, it can use only two resistors. It can use only two resistors, that is about R and 2R only. R and 2R. If we go through this complete circuit which is used to convert the digital to analog form of data, then this is having only the resistor network is with the 2R and R, 2R and R only. So anyway, we can have this reference resistance, that is a feedback resistance. Obviously we can choose according to our requirement. So now I am going with the block diagram or the circuit diagram of the R to 2R ladder type digital to analog converter. This R to 2R ladder DAC uses only two resistor values, that are R and 2R. These resistors connected in the form of a ladder. These resistors, see this one, these resistors are connected in the form of a ladder, so that we can call it is a R to 2R ladder type DAC. This digital to analog converter well suited for the integrated circuit, because they don't require the wide range of resistances. The typical values of R and 2R, if you choose the R is about the 2.5 kilo ohms, then the 2R will be the 5 kilo ohms. So the typical ranges will be from 2 to the 10 kilo ohms only, 2.5 to the 10 kilo ohms only. If I choose here 2.5, if I choose here the 2.5, it will be the 5. If I choose here it is about 10, it will be the 21, the maximum of that one only. So it works on the voltage scaling property at each node. These we can call, these are the nodes. Each node, this is a node, this is a node, this is a node, this is a node. At each node, voltage is going to be divided. This is having the 1, 2, 3, 4 nodes, and every node that is going to divide the digital data, and output will be the analog one. So that here the problem with the weighted resistor digital to analog converter can be solved by selecting only two resistors, such as R and 2R only. Then coming to the only R and 2R value of resistors are required here, then we are going with the operation of that R to 2R ladder type digital to analog converter. In the typical R to 2R digital to analog converter, 2R is parallel to 2R and it's equivalent to the series with the R. You can go with this one. See this one, 2R and R, 2R and 2R in parallel with the 2R and the 2R both are parallel, and this equivalent resistance is in series with this one, and so that we can simplify this one. That means what? The analog output voltage of n-bit data, we know that analog data will be equation that is about VO is equals to VR, that is a reference voltage, into the B1 2 to the power of minus 1 plus B2 into the 2 to the power of minus 2. This formula we have discussed in the weighted resistor DAC. Now, then operation I can explain now. This is the circuit diagram which is used to convert the digital form of data into analog form of data. Now this is the reference voltage. We can call it as a source voltage, and it is connected with the reference voltage through the load resistance to the resistance 2R, 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 and it is connected with the dipole switches. So this is the switches we can call. This is a bit 0, bit 1, bit 2, bit 3, and bit 0 is the most significant bit, and bit 3 is the least significant bit, such that you can go with the circuit diagram. It is a 4-bit converter. If you require the 4-bit converter to convert the 4-bit of data into the digital one, we require the 4 switches, and based on the number of bits we have to choose the number of switches. Now we are going with the operation now. R2 to our ladder DAC, current dependent on the bit position. See this one, it is the LSB, least significant bit, and it is the MSB. If it is having the 4 bits, and that 4 bits combinedly we can call as the a binary input, in which the least positional weight, the bit which is having the least positional weight, we can call it is the least significant bit, and this is the most significant bit, and all these are connected through the 2R, and whereas 2R are the 2R and 2R are the parallel, and where the R is connected in series. So that from here to we can proceed now. From left side to right side we can simplify it, so that we can have now LSB. Now LSB and the 2R. Now LSB and the 2 are in parallel, and these 2R and these 2 are both are parallel, and the equivalent resistance is in series with the R now. So that we can simplify 2R is parallel, but when the 2R and the 2R is parallel to each other, so that equivalent resistance is R. Now the R is in series with the R, again it is 2R. Now this 2R is parallel with the 2R, 2R is parallel with the 2R, and so that will be R, then R plus R is 2R, such that you can get up to here, this is R only. Likewise, you can go with this one. Here you can get this is about 2R, and here this is 2R, this is also 2R. So now you can have here 2R and here 2R and here 2R, and this is R, this is R, and so that by simplifying this one, R equivalent, you can get that R equivalent is equals to, and we see R equivalent is equals to 2 by 3 by R. So anyway, whatever I shared the material, everything is there, so that from here onwards you have to simplify. See this one here, this is 2R is in parallel, and so that seriously connected, that is R. Like that, if you simplify from here onwards, you have to proceed 2R and 2R in parallel, and this is in series, so that 2R that is parallel, so that you can get the R equivalent is R plus R is 2R then, and again 2R is in parallel. Then in the series this is R, now 2R, now this is 2R. Now here you got the 2R and R, 2R and R. Now here we got the 2R, here we got the 2R, and here we got the R. By simplifying that one, you can get the R equivalent in this circuit. R equivalent in this circuit is about 2 by 3 R. By substituting this value, by making use of the voltage divider rule or the voltage potential rule at the this node, we can have voltage at that particular node is equals to minus VR by 4. So such that you can simplify this one. Here we can have this is about V out by 2, and it is using what output, analog output voltage, using the Thevenin's theorem, and we can use the voltage potential rule also to get the voltage at the particular thing. This is the R equivalent, that is by making use of the Thevenin's theorem we calculate R equivalent is R, and then we can have the output at the digital to analog converter, that is V out is equals to reference, that is a feedback resistance by the resistance, that is R1 into the V reference by D0 by D16, D1 by DI, D2 by D4, and D3 by D2. That means what? D3 is the least significant bit and D0 is the most significant bit. Likewise, you can get the output that is about the analog one. Now this is the conclusion about the R2 to R ladder type DAC. Practically we can go with the V out is equals to V out, finally what we can achieve at the output side. So that V out is equals to V void is the highest value of the output by the resolution. Resolution we know that is 1 by 2 power of n minus 1. And by taking some values, and you can get this V out is equals to like this. This is about the R2 to R ladder type digital to analog converter. Advantages of R2 to R ladder type digital to analog converter: only two resistors we needed, such as R and 2R, and this does not require high precision resistors, such as we don't require the high range of resistance from 2 kilo ohms to the 2 power of 10 times of kilo ohms, so that we don't require that wide range of resistance. We can require only two resistances. By choosing the R, we can go for the 2R, that is a double of the R only. And the disadvantages, you can consider the disadvantages: lower conversion speed than the binary weighted digital to analog converter. Little bit it is going to produce the outputs lower than the weighted resistor digital to analog converter, because here we are having the circuit to make the simplification to achieve the branch currents and the nodal currents, and it takes some time to the analysis, and such that it's somewhat slow compared to the compared to the weighted resistor digital to analog converter. So in case of practical and in case of theoretical, you can verify the digital to analog converter. And next one is a inverted R2 to R digital to analog converter. It is a very simple one only. In a weighted resistor digital to analog converter and R2 to R digital to analog converter, current through the resistor changes as the input data changes. Hence the dissipate more power causes the heating of IC. This heat creates the non-linear distortion in the digital to analog converter. That means what? If you take the weighted resistor digital to analog converter and the R2 to R digital to analog converter, these are having some problems. That means what? As the input binary data changes, then the current through each and every resistance is going to change, so that there will be the fluctuations in the current, such that they creates the they dissipate some heat, and that heat may damage the integrated circuit. To avoid this problem can be avoided in the inverted R2 to R ladder type digital to analog converter. In inverted R2 to R ladder type digital to analog converter, the positions of the MSB and LSB are going to interchange. Hence, each input binary word connected to the corresponding switch, either to the ground or to the inverting terminal of the operational amplifier, which is also at the virtual ground. So here what the main difference we are going to do, we are going to interchange the LSB to the MSB, such that every bit is going to connected with its equivalent positional weight, such that we can avoid the correct fluctuations, because we are putting the resistance, we are putting the value of resistances with respect to the positional weight, such that you can avoid the fluctuations in the current. Anyway, the op amp, which is also at the virtual ground, since both the terminals of the switches are at the ground potential, current flowing through the resistances is constant and independent of switch position. And like that, we can have the R2 to R inverted type ladder digital to analog converter, and it is going to have the same circuit diagram to the R2 to R digital to analog converters only. Simply we have to interchange the MSB and LSB and the remaining bits also. So that means what? Here this circuit has the important property that current divides equally at each of the node, that current fluctuations can be equally divided in case of inverted R2 to R digital to analog converter. And with this DAC converter, that is the digital to analog converters, are completed. In the fourth unit, we left with the analog to digital converters. In two more classes, this fourth unit is going to completed. And as per my knowledge, this fourth unit is a very simple and interesting and easiest unit among all the 5 units, so that first give the more priority for the third unit, and from that direct questions are from 5 to 6 direct questions are there. If you are good at those 5 to 6 direct questions, you can get the maximum marks from the third unit, that is fourth unit, that is data converters. These are the integrated circuits which are used to convert the one form of data into the another form. By converting the one form of the data into the another form, we are getting the data transmission with the accuracy and the noise free, such that we can make use the and data converters, which includes the digital to analog converter and analog to digital converter. Thank you, students. In the next class, I am going to talk about the analog to digital converter. And from analog to digital converters, we have the 4 to type the analog to digital converters, and by studying the 4 to 5 analog to digital converter, this unit will be completed. Thank you, student.